Good morning and welcome back to my channel. Today we will explore how to apply the MultiPipe technique to Voronoi cells. I will try to provide an explanation for each step. First of all, I want to show you the final result. We can see a central ellipsoid filled with Voronoi cells in red, surrounded by a sub-D MultiPipe structure that is larger in the vicinity of the ellipsoid. So we open Grasshopper and we see how it works. Let's start by populating a 3D box, defined by a box with 100 points. Here you can see the box. Now let's create in a Rhino an ellipsoid a simple ellipsoid that has to be in the center of the box. Let's scale the initial ellipsoid twice. We scale it, choose the central point identified through the volume command here, and scale the geometry with factors of 3 and a factor of 6. So at the end we have 3 ellipses. The first one, the second one, and the third one. And then you have the box, the previous box. Okay, these are the starting geometry. Ensure that the ellipsoid remain inside the box. This ellipsoid has to be inside the box. If after scaling the ellipsoid fall outside the box, you can simply increase the dimension of the box. Okay, now we take the 3 ellipsoid and populate them with points using Populate Geometry. 2 and 3 Populate Geometry, which will create a set of points on the surface of the ellipse. Now we create a point parameter here and connect the 4-point collection to the input. First collection, second collection, third collection, and fourth collection. Remember to flatten the data because we don't need the previous hierarchy. At this point, we create the Voronoi 3D. We use Voronoi 3D to create Voronoi cells. Now, to explain the next part, let's briefly discuss the geometry of Voronoi cells and how to combine these geometries with the MultiPipe. I create this part of definition only to explain this part. So we have 2 cells of Voronoi, we have to know that to use the MultiPipe correctly, we need a series of non-overlapping lines and a series of non-coincident points, which will be my nodes. Now, the Voronoi 3D commands generates a collection of Voronoi cells, which are B-reps. Let's take 2 cells from a Voronoi collection and observe that they share a common face, some edges in common, and even some vertices in common. Our next goal will be to eliminate these overlaps And to do so, we will apply the same technique 3 times. So we come back to our definition, and we start from Voronoi, and then let's take the cell in output from Voronoi, deconstruct them by breaking them into fundamentals units, and first we have to eliminate coincident faces. To do this, identify the central points of each face and compare them to see if there are duplicates. I expect that two coincident faces will have the same central point. The cal point command gives me a collection of points without coincident points. Now I use the closest point command to reconnect these points with those from my initial collection. I use this command because it outputs the index I, which allows me to retrieve the non-coincident faces from my initial face collection. I repeat the same operation, this time starting with the edges. I identify the midpoint through the command evaluate curve, eliminate coincident midpoints, try the command cal points, and compare my cleaned list with the initial one to extract the indices to use for selecting only the edges I'm interested in. I repeat the process for the vertices. So I take the edges, uses the endpoints command. For each edge, identify its endpoints and group them with a point parameter to which I apply flatten. At this point, I apply the same technique we use for edges and faces to eliminate overlapping points. So cal points and closest point. The result will be a collection of points that will constitute the nodes for the MultiPipe. Now we are almost ready to use the MultiPipe command. The last step is missing, but we will see it later. For now, open the MultiPipe command here and connect the cleaned non-overlapping edges to the input curves. So we take the non-overlapping edges and we connect it with the curve input, and then connect the cleaned non-overlapping points to size point. So we use the result of this group as size points, and assign a value of 0.3 to strut size. This way, the linear part of the MultiPipe of the final structure will be 30% slimmer than the nodes. The last step involves calculating the value to assign to node size, to this part, to this input. I have decided that the nodes should be larger near the center of the geometry. So let's take our ellipsoid that represent the center of the geometry. So we come to the beginning. This was the center of the geometry, and evaluate its volume. So we evaluate the volume of the ellipse in order to have this output value, the centroid of the geometry. This way we will have the center of the geometry as the output. Then construct all the lines from the center of the geometry to each individual is this part of the definition was here. So we evaluate the volume of the ellipsoid, and in output we have the center of the full geometry. So we create the line, we construct all the lines from the center of the geometry to each individual node. So we go from the center to each individual node of the geometry. We evaluate the length of each one of these lines, and we use the command bounds to identify the domain that contains all the length value of the recently drawn line, and then we remap this value using the command remap to a domain, and the target domain is from 0 to 1. The starting domain is the output value from bounds. Now I use absolute to only in order to avoid some error that can happen, and then I connect I apply the graph mapper to manipulate the values. I apply two consecutive graphs. The first ensures that low-length values correspond to larger node size, and the second allows me to control how the thickness of the nodes varies. Note that I varied the value of the codomain in the second graph here, ranging it from 0.001 to 40. This value should be adjusted based on the dimension of your particular model. The very last step is to connect the output of the second graph mapper here to node size. Input of the MultiPipe. Once connected, you can have fun modifying the graphs as you like. My advice is to disable the MultiPipe before moving the graphs, so you can avoid creating unnecessary calculation this way. Now we only need to select the Voronoi cells that are inside the ellipsoid. So to do this, we take the second ellipse that is contained by the command scale. We evaluate the volume and we want to find the cells that are contained inside the second ellipsoid. So first of all, we evaluate the center of each Voronoi cells. So we take the output from Voronoi from here, and we connect with volume here. And then so we find the center. We use the point in brep command, this one, to check which points are inside the brep, and then split the Voronoi cells into two groups through the command dispatch. So we have the same cell here. So the Voronoi cell we have in L, and then we dispatch this list by a pattern that comes from the command point in brep. Group A will contain all cells whose central point is inside the ellipsoid. while group B will contain cells with central points outside of it. Now, the last thing is to apply material to the cell we found. So I use the preview command, and I attribute a reference material from Rhino. So set one material. I already prepared the material in Rhino before, and I also select MultiPipe here and connect with a custom preview and assign a material from Rhino, a black material, so I can switch from shaded view to renderized view, and this is the final results. In the central part we have the Voronoi cells that we have selected in this part, and in the outside structure is made by the MultiPipe that we made in the first part of this tutorial. If you found the video helpful for your research or work, please subscribe, like and comment on what other topics I should cover in the upcoming videos. Your feedback is very appreciated. Good work.